All right, welcome to the Differences Make a Difference slideshow. This really kicks off our Unit 5.1 on natural selection. We've already learned about artificial selection and in particular selective breeding. So we already have kind of a hint of where this is going, but now we're into the natural selection category. So nature is making the decisions rather than humans. So differences make a difference. Already, when you think differences, you should be thinking about how each member of a population has differences or genetic diversity. So as you look at this group of horses, what you will notice is that no two of them are identical. They're slightly different. Even the brown ones are not identical to each other, right? They have different colors, they have different heights. But more than that, they even have differences on the inside. They have different lung capacities. They have different hearts that are either more or slightly less effective than their neighbors. So we are made up of millions and millions and millions of differences between ourselves and those around us, even if we're in the same species. So there's two things that cause genetic diversity. Remember back to our inheritance unit, our reproduction unit, when we learned that asexual reproduction led to clones, but sexual reproduction caused a huge amount of genetic diversity, of genetic variation. So that's one of the things. The first big chunk of genetic diversity is caused by sexual reproduction. The second thing is mutations. Mutations sprinkle in differences in both organisms that reproduce through sexual reproduction, like humans and many other animals, but it also sprinkles in genetic diversity in asexually reproducing organisms. And this is how they get their genetic diversity at all. So the story of the British pepper moth. This is the most classic, famous example of natural selection that I can think of. Probably overall, it's the most famous one. So this is called a British pepper moth. You can see why. It has different splotches of, basically it looks like salt and pepper. I think it should be called the salt and pepper moth, but that's all right. I'm not in charge of naming things. So here's this moth, and we're talking, at this time period, we're talking 1700s and earlier. In the 1700s and earlier, there were many different shades of moth because they had genetic diversity in their population, but 99% of the population was white. So this picture is kind of highlighting the many different shades, but 99% of the moths were essentially stark white, okay? They really should have been called the salt moths at that point, or the powdered sugar moths or something, because they were 99% were white. And then you had some with just a little bit of darkness sprinkled in, a little bit of pepper sprinkled in. And because in the 1700s, there were these white birch trees, which were mostly white, but they had little patches of darkness in the bark. So a very, very common tree was this white birch, where you had this color pattern. And these moths survived by blending in to these trees. They would spend long periods of time with their wings outstretched, just laying on the trees, hiding from predators. And birds like to eat these things. They're delicious, apparently. Never tasted one. But if I was a bird, I would think they were delicious. Now, you initially saw this moth right here, and then maybe you also noticed this moth right here, depending on how far away from the screen you're sitting. But this moth is very, very obvious, right? Because it inherited all dark colors. So it stands out. It is not camouflaged. And if a bird flies by, this moth, there's nothing it can do about it, right? This moth is going to be lunch for sure. And this moth is going to have a higher % chance of survival. So which one of these moths is going to have more kids? Well, most likely the camouflaged moth will survive longer, which leads to it having more kids. And this moth is probably going to be today's lunch, so it's not going to have any kids. So this dark coloration will not be passed on to the next generation. This moth is probably a mutant. It had an unfortunate mutation for its environment, and it is eaten, and it does not pass that mutation on. That mutation gets stopped. But this moth inherited good traits that will allow it to survive and reproduce for longer periods of time, produce more kids, and will pass on its good traits to more children. And this is all, like I said, in 1700s and earlier England. So, like I said, if you have 9 moths and one of them looks like that, then one of them is basically a gigantic juicy hamburger for this bird. But then the 1800s happened. And in the 1800s was the Industrial Revolution. The Industrial Revolution was where we invented factories and big equipment, big machinery, and these factories pumped out the coal. So they produced smog, basically. And in Europe, this was insane. Like they had pollution problems like we cannot even comprehend in the 1800s and early 1900s in Europe, particularly these densely populated cities like London. So if you pump out all this smog for decades and decades and decades, guess what happens to the trees? These trees got covered in the soot, and they are no longer, they're still white birch trees, but now they don't look like they're white birch trees because they have been absolutely covered in this soot. So now, guess who's going to be successful? Now, again, 99% of the population looked like this white speckled moth, but then you'd have 1% that were shades of gray and black, and it was an unfortunate mutation for them, and they got eliminated quickly. But every once in a while, these white moths would still have babies, like 1% of the time. They would have babies that have those unfortunate mutations. You would get this black moth, and then that black moth would be immediately eaten, and they would always stay at about 1% of the population. They would never, their frequency would never get past 1%. But then the Industrial Revolution happens, the trees all turn black, and now who's lunch? So at this point, the white peppered moth is the obvious one. It's no longer camouflaged, and there's nothing it can do about it. Like, it has the DNA that it has, right? Now, you might be thinking, well, why doesn't it just roll around in the soot and like rub all the soot on its wings? Well, for one, then it wouldn't be able to fly, and for two, these are moths. They're not very smart. They don't invent camouflage for themselves. They just deal with the traits they've inherited, right? So this moth is now lunch, and this dark-colored moth is now going to be able to survive and reproduce. So guess what the next generation is going to have? You're going to have a lot more darker colored pepper moths surviving. So their percentage of the population is going to increase. They're going to go from about 1% of the population higher and higher and higher. But then eventually, in the 1900s, in the early 1900s, England cleaned up their act. The Industrial Revolution was still happening, but we started putting on, I guess it wasn't the early 1900s, but in the 1900s, environmental laws were passed that said, hey, you can't just pump coal straight into the air. We got to have some level of rules where, like, you can't just pump it straight into the atmosphere because it's damaging the environment. So then they cleaned up their act, and the trees turned back white. So the black pepper moths had their heyday. They had that time period where they were like the 99% of the population, and it was bad to be a lighter colored white peppered moth. But then things flipped back to how they used to be, and now being a dark pepper moth is dangerous again. So here's what we see. We have this graph, and I don't want you to just immediately abort and think that this is too hard to understand. Let's just focus on one pepper moth population at a time. So let's start with the dark colored pepper moths. In the 1800s, like in the year 1800, before the Industrial Revolution started, you see we have percentages of moths captured, meaning this is how many were spotted by people. So about 1% of the moths that were seen about 1% of them were this black pepper moth, okay, the darker colored one. But then around 1840, it looks like, 1850, the Industrial Revolution took off, and the percentage within the population of moths went from 1% to like 99%. So at this time period, it is good to be a dark pepper moth. And that lasts up until, if this is 1950, that's 2000. It looks like about 1970, around 1975 maybe. That's when the rules came out that said, yeah, we got to clean up the air, okay? Let's clean up the air, make it healthier to breathe. So we cleaned up the air and the trees turned white again. And for 100 years, more, 120 years, it was good to be the dark colored moth. But now the trees turned white again. Now you were easy prey, and you got driven back down to the 1% because it was hard to reproduce because you're getting eaten by so many birds. On the other side of things, we have this dotted line representing the light moths, the ones that are closer to white. They were thriving before the Industrial Revolution, but then once the trees turned black, they went down to like 1%. Now they were the unfortunate mutation that would just randomly happen and then would be immediately eaten up. So during this 100-year period, white moths were never higher than like 1%, 5% in the population, like this graph is showing us. But then we cleaned things up in the 1970s, and their population took off again, and today is back to where it used to be. So this is one population of moths. Like, they're all the same species. They are all peppered moths. But we have different varieties, and this graph measures the change of the different varieties within that same population. The dark variation versus the light variation. Do you see how genetic diversity saved these moths from going extinct twice? If all moths were perfectly white and there was no genetic variation, then when the trees turned dark, every moth would have been eaten, none would have been camouflaged, and peppered moths would have gone extinct. But because 1% of them had a random bad mutation that ended up working in their favor when the environment changed, now we have what would have been an extinct population of moths that is still able to hang on and survive because that 1% of the population is now more successful. Now they reproduce like crazy, and our moth population, we still have just as many moths as we used to, but now more of them are dark colored. And again, because 1% of the moths were still being created to be white, like they would get that unfortunate mutation to be white in the late 1800s, early 1900s, that for a while was a bad mutation, but because it was a variation, it allowed these moths to adapt back to the clean tree environment in the late 1900s. So this genetic diversity, having the dark and the white moths, saved the peppered moth population twice in the past 200 years. Now, a couple of key points. Did any moth intentionally choose to turn black or white? Could a white moth look around and say, hey, it looks like this adaptation that I have to be white is no longer beneficial. I should turn dark? Of course not. Plants and animals are just given the DNA that they're given. No organism can change its DNA in order to survive. No organism, no single individual can evolve. To evolve means to change over time, but it never happens to an individual. No individual changes from white to dark over time. What happens is, over many generations, the population can change as some traits are chosen to be more favorable and others are chosen to be less favorable. And when that is happening because of nature, we call it natural selection. And natural selection is the driver of evolution, okay? It's the driver of change over time. And it's usually slow, and it never happens to an individual. The reason this example is so famous and so good is because the change happened twice in like a 200-year period, 150 years even. So, and plus it was literally black and white. Like, It was a very clear change in a very short period of time. And that's what makes this example so famous. Typically, you'll see evolution or you'll see changes happening over thousands, hundreds of thousands, or maybe even millions of years. But each generation will change a tiny percent. Like each generation will be less than 1% different than the generation before it, but it will be more adapted to what nature needs at that time. And if each generation is 1% different than the generation before, then over 1,000 generations, you can have big changes in the species. Okay, hope that helps, and thanks for watching.